Great, thank you. All right, so thanks for inviting me to come out. Had a nice day talking to people. I'm a soil chemist at UC Davis, and my research is pretty wide ranging. So I've done a lot of work with arsenic, remediation, and arsenic in rice. Also done wide range of contaminants, organics, and metals, and lately have been focused on trying to get into the bioenergy cycle of, thinking about how we can use waste products before we actually develop technologies so we can have a true closed loop cycle. But today we're focusing on some of the work I've done in arsenic in rice. So we'll get started here. So arsenic, and this is the alchemical symbol for arsenic, which is one of the 11 mundane elements. This way. It's confusing. Where's the USB?
It's in the back of the left of the computer.
Nancy?
Mm-hmm.
I wasn't keyboard.
Sorry about that.
It's okay. Or it's not intense, that's the problem. It's stuck. Yeah. It's okay.
You did it.
Great. All right. Thank you. So,
Can I ask you a quick question for, what do you call it a mundane element?
I'll get back to that. All right. So for our next class, why don't you come back and tell us? Okay, so arsenic is a metalloid, which means it has properties of metals and non-metals, and so we often classify it as a metal because as a heavy metal, because heavy metals like cadmium and lead and nickel are very toxic, and arsenic is toxic. It's actually a cation, but it exists as an oxyanion. So we look at it, arsenite and arsenate forms here. And this is due to its high ion potential. So phosphate, nitrate, and sulfur. So phosphorus is actually a cation, but we think about it as an anion because of phosphate, right? And the placement on the periodic table is in group 15, and it's directly below phosphorus. And this is actually very important because of the similar chemical nature of these two elements. And this is why arsenic is actually toxic, is because it can be used in where phosphorus can be used in our bodies. So arsenic has been identified, for a long time, going back to the 4th century BCE, and Aristotle found arsenic in red lead or sandrock, and so we have it here. And Saint Albert Magnus, or Albert the Great, isolated arsenic by taking arsenic trisulfide and reacting with soap, and he was able to get arsenic out of that. So now arsenic is the king of poisons, as the title pointed out, or the poison of kings. It's also been called inheritance powder because it's been used for murder, right? And so it's very toxic, and it was a highly favored poison because it's odorless and it has high solubility. You can put it in food and drink, and you couldn't detect arsenic. It was very hard to detect arsenic. So if someone was killed by that, it was unlikely to be determined. So the Marsh test was developed in 1836 by James Marsh, and what he did was he was reacting the tissue sample with zinc and sulfuric acid, and we get an arsenic gas here, And then that's flammable, and you can put it over a flame, and then deposit the vapor, condense it onto a piece of metal, and you could look at other films of known concentration of arsenic. And so this was very specific, and the only false positive could be antimony, but arsenic dissolves in sodium hypochlorite, antimony does not, right? And so the first forensic toxicology was determined from when Charles Lafarge was found dead. His wife Marie was the prime suspect, and there was circumstantial evidence that she bought rat poison. The maid saw her put powder in his drink, and food was found to contain arsenic using other methods. But they exhumed the body and performed the Marsh test, and she was sent to prison. So that's my little history on arsenic, a little glimpse into it, which is probably in the book that you mentioned. And so arsenic is mainly found as a geogenic source combined with other elements such as oxygen, sulfur chloride, with other metals, and also exists in organic forms. So when we talk about the oxidation states, they're very important for the mobility and toxicity in the environment. And so the two most common inorganic forms are arsenite and arsenate, which is arsenite is the reduced form and arsenate is the oxidized form. Okay, and so here we have the arsenite and arsenate and methyl and dimethyl arsenic here. So these are very toxic, both of these forms, with arsenite being a little bit more toxic than arsenate. And the organic forms are almost non-toxic. All right, so where does arsenic come from? Well, it's primarily from weathering of arsenic-bearing rocks, but throughout history, we've used arsenic in lots of different products. So wood treatment, chromated copper arsenic, pesticides, fertilizers, poultry feed using this organic arsenical, roxersone, waste from tanneries, mining and smelting ores, etc. So right now, though, is the major source of arsenic that we are concerned with globally is in groundwater, right? And so that's where the problems exist, and that's why we have problems with rice today. And so arsenic itself is, this is the abundance of elements on a log scale here. We have our 8 rock-forming elements here, and we have arsenic here. So arsenic isn't rare in the Earth's crust, it's just in there, it's not, so finding arsenic should not be surprising. Arsenic is going to be in soils and has a average abundance in the Earth's crust of 1.5 milligrams per kilogram, and in soils of 3.5 milligrams per kilogram. That weathering kind of increases the relative contribution. So if we look at this map of our arsenic in groundwaters, there are certain areas of the world which have higher levels of arsenic. And globally, over 200 million people in more than 100 countries are affected by arsenic poisoning of their groundwater, which is their drinking water source. The biggest problem is in Southeast Asia here, in Bangladesh, Cambodia, Vietnam, where over 80 million people are directly impacted. In Asia overall, there's over 160 million people. So while there's 200 million, a disproportionate amount of the people impacted are in Asia. And in Southeast Asia, this is not from pesticides or anything like this. This is simply from the weathering of arsenic-bearing rocks. And the problem really started when the World Health Organization needed to address the problem of contaminated surface waters, which were, leading to a lot of illness. And so they put in millions of tube wells in Bangladesh and other parts of Southeast Asia. It turned out that the arsenic levels in these tube wells was very high, and they didn't test for that at the time. And so that's been, this groundwater came about through there. And there's a whole cycle of the weathering and the oxygenation of these materials that has resulted by putting the tube wells in that increased its mobility. But I'm not talking about that today. But the levels are up to 3,200 micrograms per liter, which is crazy because the drinking water standard in the US here is 10 micrograms per liter. So US, we have elevated levels in the Western US and Michigan, Wisconsin, Dakotas, and the Mississippi Delta, which is also an important rice growing region of the US. So this is a map of the US where arsenic soils samples are showing, soil samples, we're seeing the arsenic levels. Here's California, where we're doing, this is the rice growing region in California where my studies were conducted, and there's Nebraska, and you also have a little bit of arsenic problems. So here, over 94 public water systems are impacted by arsenic that exceed the maximum contaminant level of 10 micrograms per liter. And you can see that this is public water systems, groundwater, that it kind of comes along the panhandle and then across the southern portion. Go there. So and this is a geogenic source of contamination. Also in East Omaha, there's high levels of arsenic in soils there, in residential areas and playgrounds and such. And this goes back to the, I guess this is ARCO, AS ARCO, which had a smelting operation for lead. And lead and arsenic are commonly found together. And so because of the lead smelting, there was a lot of fallout and deposition. And so these levels of arsenic remain. And in fact, the part of East Omaha is a US EPA Superfund site where they're monitoring and cleaning this up. So arsenic is a problem in many places, including here in Nebraska. In California, over here, we have arsenic in our groundwater. So in groundwater, we have 3 to 9.5% of the testing was above 20 micrograms per liter and up to 2% greater than 50 micrograms per liter. And for the surface water, it is lower. And we tend to see higher arsenic levels in groundwater than in surface waters. Our mean concentration in soils based on 50 samples is 3.5, which is exactly the global average. So that we're not particularly high in arsenic in our soils and such. And here we can look at the arsenic in surface soils, groundwater, and rice production. And we can see that here in this region where Arkansas, Louisiana, Mississippi, Missouri, where there's a lot of rice production, also has a high level of arsenic in those soils there. So this is an unfortunate happening where we're growing our rice. We also have, high levels of arsenic. A lot of people don't know that California is actually the second largest producer of rice after Arkansas. But most of the rice grown in California is sushi rice. And so it's not used in infant foods and things where the concern of arsenic is the greatest and where the proposed threshold values are the lowest. So, what affects arsenic transport, bioavailability, and toxicity? Well, in my soil chemistry class, I say, what are the master variables of soil chemistry? And the answers are, what's always the most important thing in soil and water? pH, right? Always. And then pH and EH, so or PE. And so you can see here on an EH pH diagram that we have changing the form as we change the pH, of course, just losing protons. And then here, oxidized and reduced, we're changing the oxidation state of arsenic. And so when we are growing rice, rice is typically grown under flooded conditions. Now, it doesn't really have to be, it's just convenient because the plant can grow under flooded conditions and it helps suppress weeds. And so it works really well to grow them under flooded conditions. Most plants cannot under flooded conditions. Yields are for most rices are usually higher under flooded conditions. Some upland rice, though, it's different. So when we have low oxygen content, this is when we have our arsenite form, which is very mobile and toxic, right? And then when we have high oxygen content, so when the soils are drained, it's less mobile, still toxic, and it binds very strongly to a lot of soil minerals, particularly iron oxide, since that's one of the reasons why it's not very mobile. So in terms of how it's taken up into plants, on a really basic level, phosphate transporters, arsenic fine is taken up by phosphate transporters. So if we look at the chemical structure of phosphate and arsenate, you can see they're structural analogs, right? So the plant gets tricked and takes up arsenate when it's actually trying to take up phosphate. And then over here for arsenite is taken through the silicon pathway. So these structures aren't exactly the same here, but it's still being taken up by the same pathway as the orthosilicic acid is taken up. All right, so we end up getting reduced arsenic in the plant, which also accumulates in the grain. And so that's the concern because people consume a lot of rice globally. So one of the ways to manage arsenic content in rice is through paddy management. We can manage our paddies by draining or flooding the rice paddies, right? So when they're flooded, we go to anoxic conditions, we favor arsenite. And when we drain them, we can oxidize it and have arsenate present, right? And remember, arsenite is the more mobile species. And so this is the alternated wetting and drying example here you can see. So if we were to look at the basic idea behind the experiments that I'm going to present is that we have different types we have continuous flooding, high severity dry down, medium severity, and low severity. And we can use, we'll use different measures to determine what that is, but usually it's a moisture content by volume where 35% would be moderate and 25 or 20 would be severe. And in here, we can see that by doing this, the continuously flooded is down here. We have a low redox potential, so the system is anoxic. But if we do dry downs, we can see that for the low severity, the EH, in this case, it's actually just the redox potential, EH, yeah, is the low severity, medium, and then the high. We get this even longer period of anoxic conditions, and then once it's reflooded, we drop back down. This is simply the soil water potential for low, medium, and high severity. So yeah, you can also divine the severity by the kilopascals or water potential in the soil. So the project rationale here is that if we have prolonged flooding of rice paddies, then we have reducing conditions and we have increased arsenic-3 in the soil and water and high arsenic uptake. Now I'm throwing in cadmium here because we're going to talk about cadmium as well. And so under these conditions, there's low cadmium uptake. And so the question is, can rice paddy irrigation management be altered to decrease arsenic accumulation in rice while maintaining low cadmium concentrations? So in California, cadmium doesn't matter. Arsenic matters a little. We have high enough levels of arsenic that growers need to think about, make sure that they're not getting too much arsenic in their cadmium. We don't have to worry about it. But in Southeast Asia, cadmium is a problem. They're co-contaminants, so they have to consider both together. So this is an example of a flooding schedule. This is one with 2 dry downs. So basically we have planting, flooded conditions, drain, and then flooded again, drain, flooded again. Right, and so we have the continuous flooding treatment. So that I'm going to reference. We have continuous flooding, which is always flooded. A safe is a term used to describe a condition where the water is not allowed to drop 15 centimeters below the soil surface, so it doesn't get very dry at all. And then 35 moisture content by volume and 25 moisture content by volume. And jumping right into the results, we see here that what we have is a plot of the concentration of arsenic in year 1 and year 2. And this is the grain with the hull, this is brown rice, this is white rice. And so if we look, we pick any of these rice, the forms of rice here, and we see that the continuously flooded has very high levels, whereas the other 2 treatments here have substantially lower levels of arsenic. So you can reduce the amount of arsenic in rice grains tremendously by drying down. So you can have 2 times more arsenic in the continuously flooding. However, it's important to note that a large decrease is in the dimethyl arsenic, which is not very toxic. But we do get a reduction in arsenic-3, which is important. Now, so this is, if you're a fan of eating brown rice because of its health benefits, that's great. But it also is likely to have higher arsenic contents in it. Good news is that simply washing your rice, like filling up the pot and draining it, doing that a couple times, removes most of the arsenic. So just wash your rice. Make sure you wash it a few times. Yep. All right. Now, one thing that is important to know is that rice plants have parenchyma, which are these essentially straws that connect the atmosphere to the root zone. And so this is how they can live under flooded conditions, because these parenchyma are able to take air, oxygen, and bring it down into the root zone. Because if there wasn't any oxygen in the root zone, the plant would die. Right? And so there's a lot of oxygen in the root zone. And so because of this, under reducing conditions, iron 2 is soluble, right? And so it's moving around and it flows towards the roots. But the root zone actually has oxygen around it. So we get precipitation of iron oxides on the roots of the plant. And this is called iron plaque. And we also therefore have oxidation of arsenite to arsenate in the rhizosphere, right? Root zone, rhizosphere. And so we end up accumulating a huge amount of arsenic on the roots, right? Which then is therefore a source for perhaps reducing and taking it in. So this is the roots, like if you take the rice plant and just cut off the roots, rinse them a little bit, right? Try to get the soil off. Here we have the concentration of arsenic in that material. And if you do a treatment to remove the iron plaque, so some EDTA rinsing and bathing to try to pull off that little acid treatment, this is the amount of arsenic that is actually within the root. So this is something that I'm interested in looking at more carefully in terms of like how the rhizosphere and the oxygen in the rhizosphere contributes to a sink for arsenic uptake, right? And when we look at the difference here, this is the roots from continuously flooded, and this is from the 25% moisture content. So white versus rusty roots, right? And the iron content is here, and the arsenic content mirrors that. So when we plot the arsenic versus iron, we get this very nice linear relationship going from the alternate wettering and drying to the continuously flooded and the safe treatment. So this relationship between the iron on the plaques and the arsenic is very clear and something that should be considered sort of in the research world as moving forward and on types of ways to manage. So cadmium contamination, of course, is a real concern. Cadmium is highly toxic. And any management strategy that we do to reduce arsenic must also consider the potential impact on cadmium. And so under continuously flooded conditions, we have sulfur that's reduced as sulfide and forms cadmium sulfide, which has very low solubility. And so cadmium is not taken up. But under oxic conditions, sulfur is oxidized to sulfate. And we get cadmium sulfate, which is highly soluble. And so this is why the cadmium can be taken up under oxic conditions. So when we compare the, just picking some of the data here, year 2, we have the 25-35 safe and continuously flooded for arsenic, and then we have the continuously flooded going to 25% for cadmium. They're almost mirror images, right? And so this is obviously problematic for optimizing the system. Just adding some more data here that for the subsequent years, we basically saw the same results. And so how do we optimize this system, this really beneficial alternate wetting and drying or single dry down strategy so that we're not increasing cadmium concentration is critical. And so this is a paper that we put together, which is a review paper, but it also goes beyond that, where we model the data to try to determine that threshold where we have the optimal condition, right? And so there's I'm not going to go through and read all of the random forest regression modeling, but that's what was used. And jumping into the results here, we have the AWD effect, which is simply the concentration in AWD treatment versus continuously flooded. So if we're below this dotted line, the value of 1, we've reduced the arsenic content in this case. And so we have total arsenic and inorganic arsenic. And so we see that total arsenic is reduced more than the inorganic arsenic. And then for the cadmium data set, we see that the cadmium is above value of 1, and so that's increasing, right? So arsenic reduces the uptake. So AWD reduces arsenic uptake. So as an example here, if we compare the continuously flooded irrigation under AWD at minus 20 kilopascals, it can decrease the total arsenic from 40 to 52%. So pretty substantial reduction. Unfortunately, the cadmium increases. That's me. Sorry, I thought it was on silent. It's an alarm, that's. It's for soccer practice. Coach both my daughter's soccer teams, and it's time to get ready for soccer. Okay, all right. Okay, so now we can look at the various different variables that we choose and try to determine which variables are most influential on determining the arsenic uptake and cadmium uptake. And so for arsenic, the most important thing is the soil water potential. Surprise, but that's what came out, is so if, you know, depending on if we have a very low soil water potential, we have much lower arsenic, and the model fits the data. Vegetative state or stage is the next most important variable, followed by soil organic matter and clay content. The stage really means whether the dry down is done early in the season versus late in the season. And so we see that the total arsenic decreases, as does the inorganic arsenic decreasing. Now, going to another figure, which actually has some of the same data on it, with another line here for the predicted percent of arsenic that's inorganic. But what's nice is having them on the same plot here. You can see that the blue, which is inorganic, and red, which is total, that the decrease in the inorganic arsenic is smaller than that of the total arsenic, right? And so we can go ahead and look, if we go from minus 10 kilopascals to minus 45 kilopascals here, the predicted it goes from 50% to 75%, right, for the total arsenic, and we get much less reduction here for the inorganic arsenic. So it's really nice, and a lot of people will show this total arsenic data to show like just how extremely effective this process is. But at the end of the day, we want to be focused on looking at the inorganic arsenic. The total arsenic doesn't matter, right? Because the organic forms are non-toxic, right? So kind of coming here towards the end, we're now looking at the cadmium data. And so here, the reproductive stage or time in the year is actually more important than the soil water potential. So this is always assuming that we're doing alternate wetting and drying, right? And so the soil water potential. So the time of the year is really critical. And so here we have the blue here, where we have the blue, which is one stage of drying. So this is the reproductive stage. And so if we just do once, but if we do it twice, we get a much higher level of cadmium that's accumulated. So the AW effect is much greater. And so having a one-stage AWD implementation at minus 47 kilopascals, so we're coming now down to these arrows, represents at a late reproductive stage, right? So that's this one stage versus the two stage, is where we get the best trade-off value. So there's no difference in the arsenic here, so we don't need to worry about how wet or dry the soil is for arsenic in this region. The difference is minimal, right? But for the cadmium, it's very important to do it in the late reproductive stage with just one dry down. So here's early and late. And so we can find that this condition here is going to give us a good arsenic reduction and also a satisfactory cadmium reduction. So right now, this is the best that we've come up with for giving advice. Now, this is obviously this comes from 17 different studies out of the 1,000 we reviewed that had data to meet the criteria. And so it can't be applied to all conditions or anything, but it does fall within the conditions that we studied out of those papers. So the take-home message is that alternate wetting and drying is effective at reducing arsenic uptake. The reduced total arsenic is about 50%, but arsenic-3 is reduced only about arsenic-3 or inorganic arsenic by 30%. Now, whether or not we go to a severe dry down versus a moderate dry down doesn't have an impact. You just have to have a good dry down, right? You don't have to go to a very severe dry down to get the reduction in arsenic, right? Which, from a grower point of view, they're much more comfortable in. Growers don't want to drain their fields. It's not something they do. And so convincing them to, the less they have to dry it down, the better. So if they can just dry it down for 2 days, they don't have to stare at their field for 5 days, just thinking, oh no, when's it gonna crash, right? And so also iron plaque on root surfaces is a sink for arsenic under these continuously flooded conditions. And that the soil water potential is the most important variable for predicting the amount of arsenic in grains. And under AWD, the timing of the dry down and the number of dry downs is most important variable for cadmium. All right, so because cadmium levels increase with dry downs, this alternate wetting drying may not be appropriate for soils that have elevated cadmium. So if cadmium is more of a problem than arsenic, forget it. Don't even think about this. But if arsenic is the greater problem, then this is a strategy that could work. Okay, so 35 to 40 minutes, I think I hit it. All right, so acknowledgements, some of my collaborators, all who were at UC Davis at some point, except for Rufus Feeney, and California. And with that, I'll take any questions.
So if I was like a rice farmer, what would you suggest I do to help minimize like the cost based on your research the most?
So I guess I'd first like to know, like, do you have a problem of arsenic in your rice grains, right? So if that's a problem, then you have to think about what strategies are best for you. And so this is actually not really a financial driven decision, and it doesn't cost anything to do it. So it's really just a food safety issue. And so if you have a problem with the arsenic and not the cadmium, then I'd recommend that you consider trying it. I'd probably tell you that just take a small patty of yours and see what happens. Try it for a year. And if you aren't upset with the results in your yield, then perhaps you can expand that out to greater acreage. Yes.
Does arsenic content affect the market value of the crop?
Well, it should, right? If it's being measured, it would. So in the US, we don't have a threshold for arsenic in our food. We have it for our water and our apple juice. Apple juice because of Dr. Phil. seriously. And so it won't affect the price. I think in EU, they won't, if it's above the level, you can't, forget about it. And then I'm not actually sure, I think China has put in, levels, they do measure it. So it is important there as well. But yeah, I'm always baffled why the US doesn't have, heavy metal and metalloid, limits. So in California, spinach, and cadmium, hyperaccumulator. And yeah, sometimes the spinach, people test it and find cadmium. It's the largest spinach producer in the country from the Salinas Valley. Yeah.
You might have mentioned this, but you said that brown rice has really high arsenic content. Do other rices have similar or?
So it's all the same rice. What they do is they take the brown rice and they polish it and they remove the bran and that comes off. So the coating on the rice, the bran has a high arsenic content. So when they polish the rice and it turns, and so you just see the white, you've lost a lot of it. There's still arsenic in the white grain inside. And the hulls have the most, which we don't eat the hulls.
Yeah, I have a question that in the, like for example, in the brown rice, we are having higher content. By washing it, how much content it is going to be reduced in the arsenic? Like,
I don't
always-
have the percent on that. Yeah. I haven't done it, so I don't know, but I read it somewhere and I have no idea what the values are.
As you mentioned that like in Bangladesh and South Asian countries having higher arsenic content, and the most of the rice that is being imported to USA is from those countries. So, is USA testing for the arsenic in the rice?
I don't know that they are. You know, there's no, the FDA doesn't have a limit on it, so the Food and Drug Administration. So if the FDA doesn't, for domestic, I know that there's no control. Whether or not they test the rice for import beforehand, I'm not sure. Yeah.
As far as you know, is there anyone looking at this in terms of stacked benefits to alternative wetting and drying? Because I hadn't heard this about the arsenic piece in alternative wetting and drying, but the alternative wetting and drying gives us the water saving, which farmers usually are not interested in. But then the other piece is the methane reduction as well. And in Arkansas, they seem to be getting a fair bit of uptake around this water and methane reduction. And if you add in arsenic on top of that, with assuming there isn't that much cadmium, there's good reason to be actually supporting farmers to do this.
Yeah, so Bruce and Gabe and Daniela have done a lot of work on the methane emissions. And it definitely has a reduction in methane emissions as well. The water savings surprisingly are not that great. Because the rice paddy is a leaky bathtub, so you're always putting water in anyway. So it's the drain's open essentially.
Yeah,
But there are,
they've worked in South Asia, with Southeast Asia, it's mainly area that have done this in terms of paddy fields are a real problem in getting that, but they have come up with some techniques around that. But in Arkansas, what they're doing is they put the rice on furrows, and then it's on a slight slope, and they surge it, and then recycle the water as well. So they're not just one drying period, they're going through multiple drying periods and actually putting the water on pretty carefully.
Okay.
And they're using technology that was very common here 40 years ago. It's now been replaced with the center pivot, but it's actually working quite well in Arkansas.
So in California, do they regulate arsenic content at all or not? It's really just voluntary? whether a producer would want to adopt this?
Yeah, so there's the proposed threshold level for infant cereals, but it's been proposed for 5, 8 years, you know. There's also a proposed threshold level for cadmium for infant foods. And I don't know what it takes to actually make those go into effect. So right now, the growers, you know, they don't want to have products with high levels of arsenic in it. They just don't want to. And so if there's a way they can do it, which is not going to be costly, they're glad to do it. So, and so we get all of this research and most of, like, pretty much all of the greenhouse gas emission research was funded by the California Rice Research Board. So they're a very big commodity group and they fund a lot.
I mean, it seems like it would increase the value of the crop if you could advertise it as big low arsenic,
Right,
like organic stuff, right?
right. Yeah,
That they won't do that, that our system won't allow that.
well, they might be able to do that. Sure, there's a lot of communication between the different rice growing regions, and if California started doing that, and you know, Arkansas would be upset because they have higher arsenic. So it's just their little geography. I mean, there's nothing to do. It's not that they're doing things bad.
Yeah.
And so, you know, that would be a problem for the industry. Yeah. But if they could have a, you know, below the recommended threshold, not put a value, yeah, that could be helpful.
Any work being done on how much of your kind of people's dose of arsenic is from rice eating? I mean, presumably it can be a significant part of the amount of arsenic that you consume.
Yeah, so there are studies in Asia, and it is a substantial amount that comes from that, and you know, they actually measure it by measuring the arsenic in your hair.
So you measure total arsenic and inorganic arsenic, DMA and MMA also on the grains. Did you still find some other form of arsenic outside DMA and MMA along?
No, so MMA wasn't found in arsenic 5, also not found. And once in a while, we did detect a little, but basically it was all dimethyl and arsenite.
So almost 100% of the total arsenic was these two components.
Let's go with 99. Yeah. Yeah, because if arsenate is taken up, it gets reduced in the plant to arsenite. So.
Why does it Bangladesh have, or Central Asia have issues with farming soil? Is it another geogenic contaminant in the soil, or?
I think that it's geogenic, but there's also a lot of deposition of cadmium that comes from the atmosphere, so I think it's combined because the coal combustion leads to cadmium deposition.
And then what's the mechanism for uptake for cadmium?
Cadmium is zinc transport.
Okay.
So in Salinas Valley with the spinach cadmium problem, one of the things they do is they fertilize with zinc and it reduces cadmium.
Okay.
Buying organic matter also helps because it binds to it.
That helps explain why there's an inverse relationship too between arsenic and cadmium.
Government's very sensitive about cadmium in rice because of the international markets. They don't want it to be known that there's cadmium uptake.
Are there any other metals or metalloids that you're on your radar that you're concerned about that might enter into the picture and act in similar ways, or
Metalloids, did you, like you said?
metals or metal? You know, I just mentioned, you know, with cadmium, I'm just thinking, is there anything else that might you know?
I mean, those are the cadmium and arsenic are sort of the most common ones that are taken up into plants. And you can actually, so arsenic is the oxyanion, and so it behaves like phosphate, right? And so that's really different when you're thinking about it. But when you think about cadmium, and then we look at our other heavy metals like zinc, and then cobalt, copper, lead. So if we look at binding affinity, so the stability constants for those compounds in soil, lead and copper are bound very strongly. So like if you go to Bordeaux in France, there's a huge amount of copper in that soil because they've been using the Bordeaux blend fungicide, which is copper, for hundreds of years, thousands. And so that copper is not available. It's just held so strongly in the soil. But we move down to when you get down to zinc and cadmium and manganese, those are all like incredibly available. And so that's why we're concerned about those. And so we are also concerned about manganese in certain cases. Manganese isn't often very high, but like in California in January, there was a fire at a battery plant. And so the manganese, deposition, is a huge problem. So we have, different metals, and manganese is one of the ones they're very concerned with, in addition to copper, and cadmium.
Have you met with Hakamal Walia while you've been here?
We invited him, right?
Yeah, he was not available.
He's
He's good. He also works in the space, but also in terms of the variety of the lives and the significance of it.
Okay. Well, seeing no other questions, let's thank Sanjay for his presentation.
Day. One day. Am I supposed to pick that up?
Well, so you can also see, I have this here and I like it, so since people are still sitting here. So we made magnetic biochars to remediate soils with cadmium and arsenic, and on the left, you see the removal is really good with cadmium and arsenic. And then we are able to go in and remove the material from the soil. You can actually take the cadmium and arsenic out.
How did you get the magnetite that you're using?
It's here the methods are in the notes here for the we have 3 different magnetic jars. We added the magnetite before pyrolysis of the sawdust. We soaked the biochar in magnetite solution, and then we soaked it in a magnetite solution and repyrolized it. And so clearly this one here is bad for arsenic, the one with the repyrolized, but all the others did okay. This was a little worse off. But yeah, it's just magnetite.
You can get bacteria to make magnetite in solution too. Geobacter, I think is one.
Do they make magnetite?
Yeah,
I know they reduce it.
Yeah. Then you could maybe figure out a way to do in situ production. of
Right.
magnetite.
Yeah, and so this is not economically feasible, but that doesn't mean it doesn't work.
Yeah.
And rice is one of the few places where, because of the flooding, you can actually remove the material with a magnet.
you harvest right, you leave the roots behind, the plant gets plowed back in again. I was thinking about those plaques that build up, the high arsenic plaques on the roots. If you're constantly removing roots, would that slowly remove enough arsenic from the soil to reduce the?
It's good thinking, yeah, I mean, you would be taking it out, for sure.
They just leave the roots in when they harvest?
Um,
It's like a 2-cycle, is it 2-year crop normally, or
no, it's 1 year.
is it one?
Yeah.
You can do it for a year. So you just leave it in the ground, the roots in the ground after you harvest it.
They like to burn it, but they can't. It's a pollution.
They still do in parts of India, don't they?
Ja, det är just vanligt. Det är arsenic krossade smulvägar.
Cool start.